Hello everyone, we are Group 8 and we'll be sharing about our project Suicidal Text Detection in Social Media Posts today. Before we begin, here is an introduction of our team. I am Ethan and together with me are Zihui, Aaron, Jiayi and Ling Xiao. Here is the agenda for today. And with that, I'll be introducing our project. Did you know that 18% of youths in Singapore suffer from depression? According to the Singapore Mental Health Study, depression is the most common mental disorder in Singapore. Youths are more prone to develop depression due to chemical changes in the brain arising from puberty and from unhealthy levels of stress from societal and academic pressure. As suicide remains the leading cause of death among youths in Singapore, this becomes a concerning social issue as depression has a strong association with suicidal ideation. We believe that as avid users of social media, youths are more likely to communicate about suicidal thoughts online. Thus, this project aims to build a predictive model to detect suicidal intent in social media posts. To further highlight the applicability of our model, we aim to integrate it into a chatbot designed to build intimate conversations with youths and direct them to professional resources when signs of distress are identified. We will start off with the data collection and wrangling step. The dataset we have used is the Suicide and Depression Detection dataset obtained from Kaggle. It consists of a collection of posts from the social media platform Reddit. Our data was processed with the following steps in the sequence shown. Due to time constraints, I would like to highlight the last 3 steps done as these are catered to our project. For spelling correction, we made use of the SynSpell algorithm, which helps to correct 2 words that were combined due to the omission of a white space, which is prevalent in social media data. For stop word removal, we have retained no and not as they imply a negative intonation, which may be useful in the context of detecting suicidal intent. Lastly, although lemmatization and stemming both converts different forms of a word to a root word, we chose to use lemmatization over stemming as it considers the contextual meaning behind the word. Upon conducting initial data exploration, we found an anomalous word, filler, among the top 30 most frequently occurring words. Since this word does not contain any meaning, we removed the word. After text preprocessing, there were rows which did not contain any words. These rows were dropped. Lastly, we plotted a histogram of the word count of the posts and observed that there are outliers present. We decided to use the 75th percentile of the word count as the threshold and remove the post whose word count exceeds 62 words. The details of the final dataset after text preprocessing and data cleaning can be seen here. Now, I'll pass the time to Zihui to continue with data exploration.
Thank you, Ethan. In this section, we'll be exploring the data for further insights. To understand more about the sentiments of suicidal text visually, we have decided to use both word cloud and bigrams, which suggest a more negative sentiment. The more frequent words are kill, die, and hate, and most frequent bigrams are one die, one kill, and commit suicide. On the other hand, for non-suicidal text, the word cloud and bigrams suggest a more neutral and positive sentiment. The more frequent words are good, people, friend, and most frequent bigrams are year old and one talk. To understand more about the distribution of the average text length, we have represented it using histogram. Suicidal texts have a more uniform distribution, while non-suicidal texts have a right-skewed distribution and are shorter. Hence, we can infer that individuals with suicidal thoughts tend to be more expressive. Lastly, we plotted out the polarity score using histograms, and the range is between -1 to 1. We can see that even though both follow a bell-shaped distribution, suicidal texts have more data point on the left and are more negative, which is aligned with our earlier intuition. In this section, we'll be discussing the word embeddings used. Without loading pre-trained word embeddings into the embedding layer, our model will have to learn the word embeddings from scratch during training. The challenge comes in 2 forms. 1. Our training data could be sparse with a significant number of rare words, and embeddings learned might not accurately represent these words. 2. Our training process will be significantly longer due to the larger number of trainable parameters. Therefore, we have chosen to pre-train word embeddings which can capture the semantic and syntactic information of words. Word embeddings represent textual data in the form of a dense vector. Specifically, we will be using custom-trained word-to-vec embeddings around trained data and pre-trained glove embeddings. Word-to-vec embeddings can be used to provide a dense vector representation of words and capture information about their meaning. Its effectiveness stems from grouping together vectors of similar words, and it is a prediction-based model built on neural networks. Due to the large number of data we have, we will be building our own pre-trained word embeddings, which will also be more meaningful. Moreover, suicide is a niche field, hence we want to experiment training our own word embeddings. On the other hand, GLOVE is a count-based model that incorporates both local and global contexts. To compare between different word embeddings, we have integrated the readily available pre-trained trainer embeddings into our model. This is a form of transfer learning as we are utilizing the embeddings learned and applying it to solve a similar task. As our dataset also originates from social media, we believe that there could be some nuances captured within the embeddings which may benefit model performance. With the larger dataset used to train the embeddings, we believe that GLOVE could potentially boost model performance. Now, I'll pass the time on to Aaron to explain more about the models.
Thank you, Zihui. In this section, we'll discuss the different models we experimented with and evaluate their performance at classifying suicidal texts. There are a total of 5 models, and they are Logit, CNN, LSTM, BERT, and Electra. All models will be applied on the test dataset and evaluated based on accuracy, precision, recall, and F1 score. We prioritize F1 score above the rest as we wanted to have a balanced perspective of the model performance in terms of precision and recall. Firstly, we'll discuss our Logit model. It is suitable to classify binary variable such as suicidal or non-suicidal text, and it is used as a baseline model for comparison against other models later. We represented our text data as vectors before passing them into the Logit model as input. Here, we experimented with custom word-to-vec and pre-trained glove embeddings to represent the features. The classifier will then sum the product of input vector and its feature weight together with the bias term. The output is then passed through a sigma activation function to return us a probability value for classification. We selected the Logit model that was trained on custom word-to-vec embeddings as it produced the higher F1 score. After the Logit model, we venture into deep learning models, and one of which is CNN. We have chosen to build a CNN model as it has been proposed as an efficient way to classify text data and is capable of processing sequence of words in text. Similar to our Logit model, our text data is represented as a vector before passing it in as an input to the CNN model. This vector goes through an embedding layer that represents word vectors in a semantically designed space. Here, we experimented with 3 different inputs for the embedding layer, and they are random initialization, custom word-to-vec, and pre-trained glove embeddings. After which, 4 convolutional layers were stacked together to extract sentiments and key features that are influential towards classification. Next, we use the max pooling technique to focus on the most important features in a sentence. We have also added a dropout layer as a form of regularization to our CNN model. The final layer connects all input and output neurons together before passing through a sigma activation function to classify the text data. The best model is the CNN model trained using custom word-to-vec embeddings, as it achieved the highest F1 score. Moving on to our second deep learning model, we have LSTM. Our previous CNN model only detects local and position invariant key phrases, whereas LSTM can detect long-range semantic dependency and solves the vanishing gradient problem. With the text data on hand, we first tokenize the words into tokens before passing them into the embedding layer. In the embedding layer, we experimented with different inputs, just like in our CNN model. We have an LSTM layer next, which distinguishes itself from the CNN model. As with the gating mechanism, LSTM learns what to retain in the long-term memory and what to forget. The output of the LSTM layer needs to be mapped to our output size of 1, and this is done in the fully connected layer. A dropout layer has been added as a form of regularization here as well, after which the sigma activation layer will output probabilities of being a suicidal text. The best model is LSTM model trained using custom word-to-vec embeddings, as it achieved the highest F1 score. Now, I'll hand over my time to Jia.
Thank you, Aaron. I will now bring you through the transformer models built. Transformers are models with an attention-based encoder-decoder architecture. They have achieved state-of-the-art performances in recent research advancements. Transformers are able to handle long-range interactions better than deep learning models. Its model structure allows parallelization of tasks and accelerates processing time, unlike traditional models. Also, they yield better performance with lesser training through transfer learning. There are multiple ways to fine-tune a transformer as seen here, but we'll be focusing on training the entire pre-trained architecture, as we have yielded better prediction results after testing empirically. Let's dive deep into our first transformer model, BERT. BERT is one of the most widely used transformers today. It utilizes an encoder structure for language modeling. We have utilized the BERT-based model, which provided competent model performance within an acceptable processing time. As BERT was originally trained on full sentences, customized pre-processing was applied to our input sentences instead. BERT has two pre-trained tasks: masked language model, MLM, and next sentence prediction, NSP, which I will now further elaborate. Here's an example of an input sentence: I am feeling depressed today. MLM replaces 15% of words with the mask token. The model is then trained to replace them with the correct word, thus allowing the model to learn accurate token level representations. NSP then comes into the picture to capture sentence level information. In the training process, the model receives real and fake pairs of sentences as input, then learns to predict if the latter sentence is the actual subsequent sentence or not. The BERT model has performed better after fine-tuning. Moving on to the second transformer model, Electra. Electra is one of the latest pre-trained transformer models released. It has yielded the latest state-of-the-art performance as well, with significantly lesser computational power required compared to similar-sized models. Similarly, we have utilized the Electra-based model for better performance comparison. The MLM task in BERT only learns to predict a small subset of masked tokens. To tackle that, Electra proposed replaced token detection, RTD, where tokens are replaced with incorrect but plausible fake tokens. Referring back to the earlier example, the input will now be transformed into Henry am feeling depressed yesterday. Compared to the masked sentence, the replaced sentence makes more sense, but still does not fit in entirely within the context. The replacement tokens are first generated from a generator. Subsequently, the discriminator attempts to identify tokens which have been replaced, encouraging a more accurate representation learning from all input positions and increasing the amount learned from each sentence. The best model fine-tuned is Electra. With all these 5 models, let us now select the best performing one. As mentioned by Aaron earlier, our main evaluation metric is F1 score. Key results of the models executed are summarized in the table here. The transformer models have outperformed all the other models. Electra has achieved the highest F1 score, accuracy, and recall, while BERT has the highest precision. Although the performance of these two models matches up with one another, Electra has proven to perform better and faster than BERT, with RTD directly tackling the weakness of MLM within BERT. Thus, our final model selection will be Electra. Now, I'll pass my time over to Lin Xiao.
Thank you, Jia. Next, I'll be sharing about our chatbot integration. Youth with suicidal thoughts may be afraid to reach out for help due to reasons like social stigma, afraid of being judged, or not feeling comfortable confiding in a professional setting. According to research, chatbots can help in the early detection of suicidal behaviors as they build conversations with youth behind a screen, eroding the fear that deters them from seeking help. Chatbots are considered neural response generation models, which aim to predict a response based on input text. Next, we will be using a combination of generative and retrieval-based methods to build our mental health chatbot. The generative component of our chatbot was implemented using Logit, which is a transformer-based model that generates large-scale pre-trained dialogue responses. According to tests conducted, Logit can generate responses comparable to human response quality. However, it is unable to produce suitable responses to suicidal messages. Thus, we have a customized retrieval-based component for our use case. We've compiled a collection of comforting messages from various suicidal prevention websites, together with a list of local helplines which users can reach out to for immediate help. For every user input, the message is checked for suicidal intent using our model built earlier, and if identified, the chatbot will respond with appropriate messages. Here's a demonstration of our chatbot where users can have normal conversations with. Once the chatbot detects a suicidal intent in the conversation, it will reply with appropriate messages to comfort and provide help to the user as seen here. Next, I'll talk about our future improvements from two aspects, business and technical. From the business aspect, the first future improvement is to incorporate more languages in our chatbot to expand our outreach. We can either experiment manually the model fine-tuning process or use existing fine-tuning models that were already trained on other languages. Next is to integrate our chatbot into social media platforms like Facebook and Instagram. This could help increase our chatbot visibility and usage. For the technical aspect, the three areas that we wish to improve on. Firstly, we can employ semi-supervised learning to conduct pseudo-labeling of data points. This helps to improve the quality of data fed into the model and to ensure a more robust model. Next, we hope to integrate larger models like the Electron large model in the future, when more computational resources are available to achieve better performance. Lastly, we can use reinforcement learning to improve chatbot responses. Similar to how humans learn from interacting with our environment, reinforcement learning allows the chatbot to learn by interacting with the end users. This can help our chatbot generate better responses. Last but not least, I'll end off the presentation with a concluding note. The prevalence of depression among youths in Singapore remains a serious social issue, and early detection is crucial for timely intervention. Through our project, we have achieved our objective of detecting suicidal texts on social media platforms with the best F1 score of 97% using the LSTM model. Subsequently, we integrated the detection model into a functional mental health chatbot, allowing us to reach out to individuals in need. Moving on, we hope to enhance the performance of our detection model and chatbot, as well as expanding our outreach to more people in need. And with that, we've come to the end of our presentation. Thank you for taking time to listen to our presentation. Take care.